my cosmates. Yeah, this will be like a summarization of Math 204, MTH 204. It is to help to pass the examination, the common examination, in a very, very, like summarizing everything so reading will be easier for you guys. Okay, let's do this. Let's do it by topic. Yeah, let's do linear space. No, it is called vector space in the notes, but it is also the same thing as a linear space. Yeah, so the first thing that you will be asked at first is the definition of a linear space, of a vector space. I'm so sorry. So if they ask you what is the definition of a vector space, so this is what you should do. A vector space is a set of vectors first. Set of vectors with two operations. That is, this vector space has these two operations. We can perform these two operations on it. One, it is what we call it vector addition. Vector addition, and then two is scalar multiplication. You see, it is not complicated. So a vector space is a set of two operations, is a set of vectors with two operations. So all the vectors in this set, we can perform these two operations on them. Vectors addition, that is, we can add two or more vectors together, and then scalar multiplication. Is this scalar correct? Is this called scalar? Scale, yeah, I think this is it. So scalar multiplication, we can multiply the vectors by scalar. So at first, what is a vector? A vector is like a list of, a vector is a set of number, or even a list of numbers for, it is more like, if you learn matrices. So a vectors is just like a one by one matrix. That's the point. So vector will look like this: 1, 2, 3. Let's say we have a vector 1, 2, 3. We have another vector 2, 3, 4. We have another vector 4, 3, 5, 6, or something. Now, if you want to turn this to a matrix, all you have to do is like make it all these vectors will be your rows. 1, 2, so this, so it will be 1, 2, then 4. You see here, then here we have 2, 3, 4, and then here we have 3, 4, 5. You, although there are numbers in this vector, but they are not scalars. Okay, the number in each vector. Okay, these are vectors. I don't want to complicate things. So vectors are more like of on a plane. Vector are like a line that has a direction. So that's what vector is. But for exam, there's no need to complicate things. Just know this is what vectors look like. And if we are joining them together, then we have a matrix. So this is 3, 3, 3. So we have a 3 by 3 matrices. So we can now put a end there. Do you understand now? So this is what a vector look like. Yep. So this is a vector, this is another vector, this is another vector. Now let's say a scalar. First, before you can define a vector, we should know the field. Is a set of vectors with two in a field. Let's add in a field here. In a field, then we use this capital letter F for the field. So when we are talking about field, what is the field called? Let's say they said a field of real numbers, a field of real numbers. So it just means in this set and in this operation, all our vectors must be contained of real numbers, and all our scalars must be a real number. That's what we are just saying. If we said in the field of in the field of integers, so this field will consist of just integers. The vectors must contain integers, and the scalars must be integers. So that's what it is. So in a question, they can ask you, if we are, how can we define our scalars? Just know your scalar is coming from the field. I see this in the test question. So your scalars must be from the field. So if you are using integers, the scalar must be an integer, and also the numbers in your vectors must be an integer. Same if you are using real number. So with real number, you will see something like this. That's where we have r. So, and then when you get r to power 3, if you remember, so that's this is a space in the field of r, and then there's a 3. That's the dimension. The 3 will be the dimension, but we are not there yet. So you understand what scalar is and what vector is, right? Now, what we are now saying is, you see these vectors. I'm sorry, let me, for it to be a vector space, these two operations must be available. We should be able to add two vectors together. These vectors, we can add it to these vectors. This vector, we can add it to this vector. Then the other thing that must be available in these vector spaces, we should be able to multiply the vectors by a scalar. So we can now do 2 times a vector. So that's what they are just saying. Okay. Now let's perform vector addition and scalar multiplication. Vector addition and scalar multiplication. Our vector is 2, 3, 4, right? This is our vector here. And now we are now saying this vector times 2, or 2 times that vector, they are the same thing. How do you do it? So to do the multiplication of this is what you do. It's just you have a vector here. Now each number in that vector must be multiplied by 2. You should just multiply it by 2. That's what we are just doing. 2, 3 times 2, then 3 times 2, then 4 times 2. So that's it. And with that, you have 4, 4, 6, 8. And that will be our new vector. So this vector multiplied by 2 will give us this vector. So now let's not do that and do vector addition. So this vector plus that vector, what's the answer? No, enter, bro. So this vector added to this vector. So this one, so let's call this u. So we can now say u plus v. Okay, do you understand that? So let's do u plus v. How do we do that? So in this tutorial, our vectors will be represented by capital letter, while scalars will be represented by small letter. In your exam, you use some kind of, an arrow. So you can say this is a vector and it has a direction. That's what the arrow stands for. But let's move forward. Now, to do 2 plus u plus v, this is u and this is v. All you have to do is just add the scalars. So we can say the number in the vectors are scalar, right? Add the scalar in each position. So to add two vectors, they must be of the same size. So this is what you do. The first number here, add it to the first number there. That's the first one. Then the second number, add it to the second number there. That's the second one. And the third number, add it to the third number there. And that's the fourth one. So you have 5, 7, 9. So that is how you add two vectors together. So to add the two vectors, they must be of the same size, and it is pretty straightforward. So we know what vector addition and scalar multiplication is. Now, they say, let's continue with our definition of a vector space. So just put this in your head, go to the exam hall, and everything about all this information are also important for the next step. So that's why I'm explaining everything. So they must have this vector space is a set of vectors in a field F with two operations, vector addition and scalar multiplication, and must follow these axioms. The axioms can be 8 or 10 depending on how you are defining it. So, but let's just say these axioms and see how many we can generate. The first one is the closure. In your head, just remember, say the first one is the closure. Then under this closure, you can now divide it, you can now derive 2. So the first one is closure under vector addition. So you see that addition, okay, let's define something for u v w, and we can now do a b c in in F, in that field. If you remember, our F is field. The way you write this in real life will be different. So just remember, the F is written in a special way. You can put an arrow on all these your vectors, and this will be your scalars. So now, for we have all these vectors in this field. We also have all this scalar in this field. So we'll be using all this in our exams. Closure under addition. So if you take two vectors, okay, if you take two vectors, let's say, let's do it here. Let's say u plus v, that's our two vectors. U plus v must be in our field. So that's also what we are saying. I hope I'm communicating, guys. So what we are just saying is, no, let's not call this f. Even using capital letter for all these vectors is because this v, we use it to represent our vector space. So let's do something like this arrow we are not see here. So I'm using my computer, so let's use k or l, anything. It is just, you are just representing it. So you should just know, you should write this in a different way. So this v is not our field, it is the vector space. So for u, l, w, a, b, c in our vector space, so all these things must be must be available in the vector space, or or the vector space must follow all these axioms. I'm sorry. So it should be in. So the E will be capital letter E that I'm using here. But if you remember, it is something like, okay, I think I should be able to draw now. So let's draw instead. So let's do this. So instead of using that E, so this is the E that we will use. This E, this is it. So remember to use that here. Now let's continue. No, I know they draw again now. So you see, UV must be in what? Must be in that. Let's use a hand. So UL must be in V. So let's see how this look like. You see now, closure under vector addition. So U plus L must be give us a result that is in V, that is in our vector space. So just remember, I'm using this capital letter E for something like this. So you should know what you are doing. Yeah. Now, number two, we are taking a lot of time already. Closure under uh, scalar multiplication. So we have two closure rules, right? Like that. Yeah, that's correct. So it must be closed under scalar multiplication also. So we do something like So we take a scalar here, A, and then we take a vector U. This sign, so I represent like this, must be in V. So A times U must be in V. Do you understand? Just so they must be closed. The vector addition must be closed. What we are just saying about closed is if you have two things, if you add two things together, the result must be in that vector, must be in the vector space, sorry. And then if you multiply a vector by a scalar, any scalar in that field, they must be in that vector space. Now let's move forward. The next thing now is associativity. In your head, you don't need to write all this associativity down. So now the next thing is, we now said, oh, let's do commutativity first. Commutativity. Now the first thing now is, this one is additive. So number 3, additive commutativity. Yep. What this is just saying is, take a vector U, add it to another vector L, must be equals to just in the direction. So that's it. You see, it is not hard. Additive commutativity. Yep. So the next one, associativity. The next one will be additive associativity. Now, what's our associative law? U, so you need 3. So U plus L, no, let's do it this way. U plus L plus W will be equals to what? Just put the first two, U plus L plus W. So you just say, no matter what you add first, if you're adding 3 vectors together, they must give you the same result. If you like, add the first two first, then the third one, or add the last two first, then the first one. Anyone you are adding first, they must be associative. Yeah. So, and then there's also associativity for multiplication also. So, so the fifth one is multiplication. Yeah, multiplication of scalar. Okay. 5, associativity of scalar multiplication. Now, what this one is saying is, let's have see, A times B times a scalar must be equals to A times B, see here, AB, or you put them in bracket first, AB times that scalar. So that's what it's just saying. You see, so this is associativity for scalar addition. This is this is associativity for vector addition, and then this is associativity for scalar multiplication. You see, now we have 5. So if you just save this in your head, we have closure, we have commutativity, we have associativity. Now the next thing is to think about inverse. Inverse. So inverse, we call this number 6, and then we can now say additive inverse. So if So for each u, there exists a minus u. Remember, the way you write your scalar is different in real life. Please, this is important. There exists a minus u where u plus minus u will be equals to 0. We can prove this. We can prove everything here, but let's prove this additive inverse first. We said for every u, this is our u here, and this 0 is not just any 0, it is a 0 vector, if you remember. So it is a 0 vector. So that is, everything in that vector will be equals to 0. Remember to put that arrow on top of it. So it is a 0 vector. So everything under it will be a vector. So if you want to prove this number 6 real quick, let's say we have 2, 3, 5. They said for every kind of vector like this, there exists another vector that looks like this. That will be minus 2. We are just saying minus of this, minus 3, then minus 5. And it must also be in that vector space, I mean that field. So these are integers and this is also integers. They are also real numbers. Now if we do this, let's say this is our u and this is our minus u. So u plus minus u should give us 0. Minus u should give us 0. Now let's prove it. This will be 2 plus minus 2, 3 plus minus 3, and then 5 plus minus 5, which is just saying 5 minus 5, 2 minus 2, and all. And at the end, you have 0, 0, 0. So that's what it's just saying. Yeah. So that's the additive inverse. Now we have the identity rules, identities. So first, let's talk about the additive identity. So all this is just saying, so this will be our number 7. So there, in our vector space, there exists a 0 vector where that 0 vector plus our u or any vector will still be equals to u. You can also prove that if you add 0 plus all we have shown that time, it will still be the same thing. Now there's also multiplicative identity. Yep. Multiplicative identity. So there also exists a 1, or when you do 1 times u will be equals to u. As we said that time, if you create when you have a 1 and you multiply it with u, it will give you u the same, and it will still be the same thing. Now we said it is 10, so there remain distributivity. So first, distributive over vector addition. So no, this is 9. What we are just saying is, when you multiply a scalar with the addition of two vectors, let's say u plus l. So when you multiply a scalar by this, so when you multiply a scalar by the addition of two vectors, all you will get is a times u plus A times L. That's just distribution. And then there's also distributive over scalar addition also. So now let's do this the opposite. And you can prove all these things yourself. If you're asked to prove, you can ask to prove any of these axioms, so you can prove it. So now let's do. All you are going to do is bring a vector here, then there exists some scalars inside here, and it should be equals to just the same thing, a times b plus, what's the next one, u times b. So that's it. So this is distributivity through distribution. As you can see there, that if you save this in your head like this, closure, any vector you add together must be in the vector, and any scalar multiplication you do must be in the vector. Commutativity, additive commutativity, u plus s must be equals to l plus u. Associativity, additive associativity, u plus l plus w must be equals to u plus l plus w. You can see it is just the same thing. So associativity of multiplication, of scalar multiplication. So a times b times u must be equals to a times b, then you times it by u. So what you are just saying is anyone you times together at first, at the end, if you multiply it, you will still get the same thing. So we have inverse, additive inverse. For each u, there exists the minus u, where u plus minus u will be equals to 0. Then we have the identities, the additive identity, 0 plus u equals to u. Multiplicative identity, 1 times u equals to u. Then we have the distributivity, distributive over vector addition and distributive over scalar addition. Now let's move to the next one.